This video is looking at grouped frequency distributions. We're going to look at some definitions for it, and then also we're going to look at an example. Now, the reason grouped frequency distributions are important is most of the time your data is not going to lend itself to be ungrouped. Usually you're going to have a wide enough spread of data that you can't afford to have each data point be its own class. So in this case we have to do some kind of grouping. So that's the target here and the goal here. In order to look at this, we have a handful of new definitions we would need. We're going to need the idea of a range, which is simply the high value minus the low value. The book spends a lot of time on boundaries versus limits. Don't get too tangled up in that. Those are just the, for lack of a better word, edges of the class, and they're done slightly differently. I'm not going to be testing you on the difference between the two, so spend your time looking at the overall picture rather than at those nuances of limits versus boundaries. Just a couple things. The limits typically are going to be shown are the same precision as the data. So if your data is whole numbers, your limits are whole numbers. Your boundaries, on the other hand, are 1 decimal place more than whatever your data is. So if your data is whole numbers, boundaries have 1 decimal place. Final definition then is the idea of the class width, and to do that you take the upper boundary minus the lower boundary. And I'll show you an alternate way to do it with the limits whenever we get to the example. Okay, now, some rules for building group frequency distributions. First rule is mutually exclusive classes. Now, mutually exclusive classes is math speak for your classes don't overlap. If your classes overlapped and you had data where they overlap, which class would it go in? We don't want that. So, rule number 1, they can't overlap. Rule number 2, your classes need to be continuous. There can't be any gaps between them. If there were gaps between them, data could fall between. We don't want that. Now, 1 and 2 work together to give us number 3. Number 3 is that your classes are exhaustive, which means all data has a class. So that, by saying they don't overlap and they're wide enough, continuous, no gaps between them, all data should have a class. Then the final thing, number 4, the rule, classes should be of equal width. Now, there is one caveat to that. It's permissible to have an open-ended first class or an open-ended last class, or both. So, for instance, if you were looking at a survey where the age ranges are 0 to 19, or less than 19, 20 to 29, 30 to 39, and then maybe at the top they go 70 plus. So that less than 19, or up to 19, and the 70 plus would be open-ended. Whereas all those classes in between need to be the same width. Now, typically the recommendation is 5 to 20 classes. I got to tell you, 20 is a lot. Typically 12 or fewer is probably a better bet. The book recommends an odd class width. The reason for that is because then you have a midpoint that is the same precision as your data. Again, not a critical point with today's modern tools. All right, now we're going to look at an example, and this example is actually similar to example 2-2 in the book about record high temperatures. So if you're looking at this, hopefully between looking at that example and looking at this example, you'll be able to figure out and see the patterns. Okay, the first step, we want to determine what our classes are. And to do that, we're going to look at the highest and lowest values and compute the range. We have to select a number of classes. We have to figure out how wide the class will be. Then we have to go through, set up the limits and boundaries, tally the data, and then find the frequencies and build our cumulative frequency graph. Now, one thing that I think the book doesn't really cover, and I think it's an important step in the real world, in step 1, if you have naturally occurring groups for your data, you probably want to use those. And the book doesn't really mention that, and that's one of the reasons why I bring up example 5 and show it the way that I do. All right, so we'll jump to the example. Example 5, construct a group frequency distribution using the following data representing the ages of Pittsburgh Pirates. You may notice this data is fairly old. The reason for that is because the data from 2006 actually has couple of things that don't exist in the current data, so it actually demonstrates better with the 2006 data than it does with the current data. All right, so after we build the distribution, then we'll also build some graphs. All right, now just a couple of things. The book, the items on the x-axis or the horizontal axis for a graph. On a histogram, it's boundaries. Frequency polygon, it's the midpoint of the class, and we'll look at that when we build it. The ogive is also boundaries, and they typically show you plotting points at the upper boundaries. And now, one of the reasons I told you not to get too tangled up in the boundaries, the book spends time on the boundaries because of this graphing. Excel doesn't honor it very nicely. So, with today's tools, you don't build graphs like this, so it's less of an issue. The book was written like this when I started using it in 1992. Through all these editions, they've never really changed that. So things were a little bit different in 1992 computer-wise versus now. All right, so that takes care of setting it up. Now, if we want to actually, apologize there for juggling things around. If we take this data, we want to build a frequency distribution with 5 classes. Okay, I, in this case, fairly arbitrarily chose 5. That's another step while you're thinking about it. How many classes make sense? Okay. Now, first thing we do is find the range. So we have to go and find the high value, and the oldest person in this data is 41. This is the reason I still use the older data. The pirates don't have anybody in their 40s right now. The lowest age in the group, excuse me, was 22. So the range of data is 41 minus 22, or 19. Now, to find the class width, you take your range, divide by your number of classes. You look at that result. If that result comes out to have any decimal on the end, you need to round up. So in this case, we came out with a 3.8. We need to round that up, and our class width is going to become 4 because we want our class width to be the same precision as our data. Even if this had come out to be 3.1, we still would want it to be 4, because if we lowered it down to 3 and made 5 classes, we wouldn't have a place for this highest value. It would be outside the top range. So that's why if this had come out to be exactly 3.0, we could have left it at 3. But if it's got anything after the decimal, we need to round it up. So in this case, we round up to 4. Now, we need to find the lower limits. So we start with our lowest value, 22. And then we're going to add our class limit, or I'm sorry, our class width to that. So I'll scroll down here to the table. So our limit for the first class is 22. Add 4. Lower limit for the second class, 26. Lower limit for the third class, 30. Excuse me. Add 4 again, 34. Add 4 one more time. Lower limit of the fifth class is 38. Now, to find the upper limits, we look at this 26 and say, all right, we got to back off 1 down to 25. So the upper limit of the first class is 25. Now we can do the same thing. Add our class width again. So 25 plus 4 is 29. 29 plus 4 is 33. 33 plus 4 is 37. 37 plus 4 is 41. Okay, now, said that the limits would be the same precision as the data. The boundaries will be one more decimal place. Now, if you really want to figure out where these boundaries are coming from, we need to meet in the middle between the bottom of class 2 and the top of class 1. So halfway between 25 and 26 is 25.5. And you'll notice that the upper boundary of class 1 and the lower boundary of class 2 are the same. So same way, between 2 and 3, between 29 and 30, 29.5. Between 33 and 34, 33.5. Between 37 and 38, get those. To get the lower one, subtract your class width from the upper boundary. So 25.5 minus 4, 21.5. 37.5 plus 4, 41.5. Now, the nice thing about the boundaries is if you do the subtraction, you get the class width. If you look at the limits, you say, well, you know, when I subtract them, the difference is only 3. The reason is because it's accounting. In computer science, there's something called a fence post error. The span from 22 to 25 is actually 4 numbers if you think about it. If you count them off on your fingers, 22, 23, 24, and 25. So even though the subtraction is only 3, it's actually 4 numbers. So both of these give you a width of 4. It's just a little more obvious with the boundaries. To find the midpoint, you can take either way. You can either do it with the limits or the boundaries. I would usually use the limits because it's simpler numbers. Take the lower limit, 22, plus the upper limit, 25 is 47, divide by 2, 23.5. So meet in the middle. So do that for each class. Now, once you have these limits and boundaries, walk through your 25 pieces of data and assign them to the classes that they fit into. So everybody from 22 to 25 goes in this class. Everybody from 26 to 29 goes in this class. Exactly the same as what you did with ungrouped, except that you're targeting a range instead of targeting a single number. Build the cumulative frequency column exactly the same as we had in the ungrouped. You take the first class is just the same as the frequency. Second class, add the first 2. Third class, add the first 3. Fourth class, add the first 4. Fifth class, add them all. Okay, so that's the group frequency distribution. To build the histogram, same basic thing as you would do with the ungrouped. As I said, Excel doesn't do this very nicely. I did this to show matching the book. I'll show in just a second a more real-world approach to doing this. So you have the lower boundary to the upper boundary. In the book, you'd see these bars touching. As I mentioned earlier, Excel doesn't do that by default, but you can clearly see the heights, 10, 10, 1, 3, and 1. The frequency polygon, line graph showing exactly the same thing. The one difference being that in this case, we were graphing against the midpoint. Again, not a big deal. And note that the axes are labeled. Now, the difference between using a histogram, using a frequency polygon, is purely a matter of personal preference. They show exactly the same thing. If you overlaid these two on top of each other, they would match up exactly. Now, the one advantage to a frequency polygon is, you'll see in the book, there's an example. You really shouldn't cut the bottom off of bar charts because people look at the ratio of the heights. So if you have to cut the bottom of a chart off, you're better off with a line graph.